All right. Hello, AppSec Days Pacific Northwest. Hope everybody is excited and caffeinated enough to keep going. Our next speaker is Gary Schneir, VP of Software Architecture at Ubiq Security. And Gary is presenting Format Preserving Encryption, How to Encrypt Sensitive Data Without Restructuring Your Database. Gary has over 35 years of experience in the technology industry with a concentration in cryptography and software architecture and design. This provides him with a deep understanding of how to build secure, resilient software and systems and leveraging cryptography in a safe and effective ways. Gary is very passionate about simplifying cryptography and encryption so that software developers and security teams across the globe can build security into their products and applications by design. Gary is co-inventor on 18 approved and granted patents and has spent his career serving both the private and the public sectors, including classified work for the US Department of Defense. We would also like to thank our sponsors who made this conference possible. And with that, over to you, Gary.
So, as I said, let's just do a quick little summary of encryption. The purpose is to secure data. I mean, an observer should not be able to distinguish encrypted data from random data. Okay. So there's a lot of different ciphers out there. I mean, I'm throwing out a couple of them here. I won't go, I'm lost a little time, so I won't go into much detail. But not all ciphers or modes are created equally either. So AES is the one that most people think of when they think of encryption. And AES, it can provide excellent data security. It's really the result of a 5-year selection process that evaluated something like 15 different competing designs and became a standard in the early 2000s. AES superseded data encryption standard DES from the 1970s. So think of AES as a tool, but as any tool, especially an encryption tool, you need to know how to use it properly, okay? And you also should know its advantages and limitations. So hopefully some of you realized in my previous slide, the wording when I said AES can provide excellent security. There's a lot of different cipher modes, and I'm going to pick on ECB right now, electronic code book, and on the surface, it works very well. It says it divides the message into blocks, and each block is encrypted separately. However, each identical plain text block produces the same ciphertext. Okay, so what that means is something like this in Tux, where we have lots of little blocks, but a lot of the blocks are the same, like the blocks that represent white or the blocks that represent black. For the image, if I encrypt one of them by itself, that's fine. But when I encrypt them all and I look at it as a group, then I've got a problem. You can see, even though this is encrypted, I can really tell information about what's behind this. Okay, so let's also talk about encryption cost. And I'm not just talking about the CPU, because almost all modern CPUs have built-in AES instruction sets. Okay, but there's more to it in relating to storage costs. So there's initialization vectors, authentication tags, padding, counters, nonce. All of this can go into some of the cost of encrypting data. So if I look at a very simple case here, where I'm taking very small string of 11 characters, running it through OpenSSL with some passphrase, this produced 45 characters of base 64 encoded data. Okay, the raw binary data is just 32, but 11 characters became either 32 or 45. And that's where I'm hoping you came to this. I mean, I've been on calls where everyone says, well, I want to encrypt data, but how am I going to avoid restructuring my database? And a lot of people have said, we restructure our database. Okay, so hopefully I'm going to give you some information on how you can avoid that. Okay, and again, the 32 bytes would have been even more if we had been using AE/AD ciphers or authentication tags, etc. So again, getting back to the problem and the topic of this presentation, how do I take something like a 9-character US Social Security number and store it back into a 9-character field? Okay, so again, using the OpenSSL, I've got a simple 9-character string. I run it through and I still get the 32 bytes or the 45 base 64 encoded characters. How am I going to write that back to a 9-character string? I mean, the simple answer is you're not. Okay, and to make it worse, because of some of the IV and some of the other things, we really need much more than just those 9 characters. Okay, and I'm showing the base 64 because you've got to be concerned about the 32 bytes, which could be unprintable. They could represent a string null terminator. They could be a continuation character for a UTF-8 string. So you really have to know what you're going to be writing. Okay, that's where format preserving encryption comes in. Okay, first of all, it's a NIST standard. Granted, it's in draft form. And as I said earlier, AES was the result of a 5-year selection process. So it may still take a while to get into final form, but FBE allows a number to still look like a number, or a string to still look like a string. And a date may still look like a date, and I'll dig into that more later. And fortunately, punctuation or spaces or dashes will still occur in the same location. So here's a simple example of a or data that represents a social security number, running it through an FBE algorithm, and that 756 still looks like a social security number. Anyone looking at it would think, yeah, that may be a legitimate social. Okay, and one thing about FBE is it can probably still be stored back into the database without modification. And the reason I'm saying probably is during my career, I've been a DBA, and it was common for me or for other DBAs to write triggers or constraints to prevent invalid data from being written into certain fields. Let's face it, I wanted a pristine database, no garbage allowed. So the question is, did your database administrator get aggressive and write triggers to reject invalid social security numbers? Okay, and it's not well known what the format of social security numbers, at least by developers. They may think, hey, any 9-character or 9-digit value is a social or is a valid social, but that's actually not true. Okay, and there's very specific invalid formats. So the first 3 cannot be zeros, the last 4 cannot be zeros, the middle 2 can't be zeros, can't begin with 3 6s, and there's other series that are invalid as well. So if you think about what format preserving encryption is, we're going to make it look random. So if I look at just that middle 2 characters here, 1 out of every 100, I'm going to end up with 0 0. So did a database administrator write a check for this and create a constraint that's going to fail? Okay. With FBE, it's probably going to be an easier discussion with your database administrator and say, can we relax these constraints rather than say, oh, you know that 9-character field, I need to make it a 256 varchar in order to support all the padding and everything else that goes along with it. So why haven't you heard more about FBE? Okay, you may have. I'm hoping a lot of you have. But remember, it's still in draft form. Okay, and it's going to take some time to work through. And the original proposal was 3 different methods, FF1 through FF3. Okay, it's been revised already, and FF2 was removed. And FF3, they've revised it and created what they call FF3.1 or -1. And some of these algorithms, FF1 and FF3-1, have very different constraints. As an example, FF3-1 for a binary string, a string that just contains zeros and ones, it can only support a string that's 192 characters long. And if you want to get something more realistic, like a base 62, which is mixed alphanumeric, mixed case alphanumeric, it can only accept a character string that's 32 characters long. And that may work for a social, but there's a lot of data that won't work for. Okay, and yes, a longer string could be split into smaller blocks and encrypted using the FF3-1, but that takes a little bit of planning, a little overhead. You need to know where to break it, etc. And another thing FBE doesn't do is it doesn't support AEAD. And simply put, that is a way for the encryption or the cipher to recognize whether the ciphertext has been altered or if the incorrect encryption key or decryption key is being used to try and decrypt data. And if you think about it, for someone who's storing social security numbers or bank account numbers, it's important to know, did I get attacked and did someone alter a bank account number? Or did someone use a wrong decryption key to decrypt a bank account number, which all of a sudden causes money to flow into the wrong account? So it's something that FBE does not support, but again, that doesn't mean you shouldn't use it or consider using it. Also, metadata, because of the limitations, you want a string to look like a string the same length, there isn't other metadata that you might normally associate with a ciphertext. So now let me introduce you to enhanced FBE or EFBE. And no, NIST hasn't created a new standard, but it's based on simple cryptographically safe pre and post processing of the ciphertext produced by FBE. So we encrypt in one character set, and then we map it to another. So as an example, we might encrypt using base 10, and then we map this to a character set of 36 or 62 or something similar. And if the output character set is sufficiently larger than the input character set, and the minimum string length is long enough, then less bits are needed to represent the same data. So as an example, 9999 in base 10, if I convert that to base 36, I only require 3 characters worth of data. Okay, so that gives me a whole extra character. Remember, FBE requires the same number of characters in and out. So I've got another full character to work with. So I can use that for any metadata that I want. And as an example, I could use it for representing a key number. So using a leading 0 would be a 1, or key 1, or a 1 would be key 2. So I've already talked about some of the other limitations, but hopefully you're already having some things in use cases in mind for FBE. You may have struggled and said, I want to encrypt, and I'm using AES 256, and all of a sudden you realize you can't write it back into the same database. So you're thinking, hey, FBE will solve my problem. But there are some limitations. There's some data requirements regarding min and max lengths. There's some relationships between the radix, meaning the input and output character string lengths. And as a simple example, the input radix put to the factor of the minimum length has to be greater than 1,000,000. So simply put, a simple 5-character zip code can't be encrypted using FBE. Okay, it just doesn't meet the NIST requirements. But zip +4 works fine. Okay, FBE is computationally intensive, so it uses a lot of big int libraries. And unfortunately, in many languages, the big int libraries and radixes aren't standardized. So base 10 works fine, hex works fine, base 36, meaning single case alpha and numeric, probably work, but mixed case alpha probably doesn't. Okay, also, as I explained before with the social security number, if I'm doing an encryption of a date, like here's today's date and year, month, day, the FBE is going to produce numbers, but they don't make syntactic, or they may not be syntactically correct for a date. So in this case, the month and the day fail. Okay, some other pitfalls. Okay, if I'm doing encryption of a simple string and I've got space characters, well, here's my data. I want to write that out to a database field, read it back in. But what happens in a database that has a varchar, where trailing spaces get truncated? Or if I wrote it to a car field and it added spaces. Okay, here's a simple inequality, okay, that holds true for FBE, and it's an important thing to understand when you're going down this this path, is that every character matters. Okay, so and it's not just a simple case where if I forgot the space, I'm going to get A, B, C, D, E, and F gets truncated. No, I'm going to get something completely different. Okay, and if you're storing a number, if you're going to go take a number, convert it to a string, and go back to a number, leading zeros matter as well. Okay, we already talked about leading zeros, but what about numeric overflows? If I've got a database field with 32 bits, I can support 4 billion. I've got a number, let's say 1 billion, I encrypt it, it comes out to 9 billion. What's going to happen when I try and scroll that into the database? Okay, will it truncate? Will it round? Will it fatal? It's just something to be aware of. Important thing to know is encryption keys are typically used more than once. And typically that's okay. Okay, in AES, you use the initialization vector to get around that. With EFBE, we allow the encryption key to change over time, so that helps as well. But the tweak, which you can think of as an initialization vector, need to be managed or stored externally. Okay, so why is that important? Well, the same zip +4 will encrypt the same with the same key and tweak. Okay, and if someone is looking at your data, zip codes may have a population of 10,000, or they may have a population as few as 1. So if someone were to get your data, they can do some statistical analysis if you are using the same key and same tweak all the time. Okay, so what's all this mean? Okay, AES and FBE or EFBE are tools to use when securing your data. Okay, FBE is not going to replace AES, plain and simple. Okay, but they're both suited for different use cases. I like to think of FBE as well suited for structured, or something going into a structured database, and AES being used for something that's unstructured, maybe going to a file or an S3 bucket. So again, AES is a better choice when the data is long object, binary or text, it doesn't matter. Okay, the storage is not as constrained, again, maybe going to a file system or S3. And the storage cost of the padding, the IV, the algorithm is not a significant percentage of the ciphertext. Okay, if you're paying per megabyte, if I've got an extra 50 characters for other information, that's not going to matter. Okay, FBE is better suited when the results need to look similar to the original plain text. Okay, the data storage cannot have significant changes. Again, maybe we're relaxing a database constraint, but we're not changing a char 9 to a varchar 250 and all the programs that have to interact with it. We're leaving a char 9 as a char 9. All the programs that have a fixed length processing of that data can work without changes. Okay, and again, as I said, we might relax the constraints, but we can still keep it as a char. Okay, here's a quick little demo just to set the stage. We've got an input character set of 0 through 9, representing a social security. Our output character set is mixed case alpha. and we've got pass-through characters of a dash, a space, and an underscore. Okay, and I'm using EFPE for this. So when I run the encryption, this is the result. Okay, you can see the leading zeros are because of that lossless compression, which I could use to embed additional information. Maybe it's a tweak, maybe it's a key number, maybe it's something similar. Okay, similarly, if I want to decrypt, okay, again, the same, just tell it to decrypt and give it the same data. I know I went through that real quick. I apologize for sort of the initial technical issues with my laptop and Zoom, but any questions?
Thank you so much, Gary. I haven't seen any questions in the chat, so if you have any, it's a good time to post them. Maybe we'll give half a minute to people to catch up. Still nothing. Maybe I'll ask the quick question. If somebody wanted to connect with you, Gary, what's the best way?
My email, it's gary@ubiqsecurity.com.
Okay, so everybody, if you have any questions, you can follow up with Gary afterwards. And with that, we're gonna switch over to our next session. Gary, if you can stop sharing your screen, please. Thank you. Thank you so much. It's been very interesting. I haven't been exposed to the format preserving encryption before, and I've learned quite a lot of things. Thank you.
Thank you.